Welcome back to Fun with Crypto. Hi, Brent Bilger again, and still Director of Technology at Verizon, and still these words are mine, not Verizon's. In Part 2, you'll get a gut-level understanding of symmetric key encryption with message integrity. The objective is to take some arbitrary plaintext, apply a cryptographic algorithm to it to generate some ciphertext that can be transported across an untrusted network and decrypt it with the same key to regenerate the plain text that we started with. To understand this better, let's create a make-believe stream cipher with this stream of bits generated from some pseudo-random number generator. In a later video, we will see how the Galois counter mode algorithm transforms the AES block of cipher into a stream of bits like what you're looking at now. Okay, let's add some plain text that we want to encrypt. And we will divide the plaintext into blocks of 3 and assign decimal numbers to each block to make it easier to see what's going on. Here we see that our plaintext represents the numbers 0, 1, 2, and 3. The stream cipher encrypts the data by doing an exclusive OR of the plaintext with a stream of bits to generate our ciphertext. As we'll see in a bit, the exclusive OR function is reversible and will allow us to use the same stream cipher of bits to decode the ciphertext back into plaintext. For now, note how the XOR algorithm works. 0 XOR 0 is 0, 0 XOR 1 or 1 XOR 0 is 1, and 1 XOR 1 is 0. Translating the ciphertext into decimal, we see that the data is truly different from the plaintext. Now, we can transport the ciphertext across the untrusted network, knowing that an observer cannot determine the original plaintext from the ciphertext. At the receiving side, we regenerate the bits of the stream cipher using the same pseudo-random number generator. Now we can XOR the ciphertext with the bits of the stream cipher and voila, recreate the plain text. Let's look back at the left side at the plain text bits that did not change in creating the ciphertext, and on the right, the same bits do not change. Then on the left, the bits that did change, and on the right, the same again. You may want to stop the video and check out how the XOR algorithm creates this awesome feat. Okay, we succeeded in providing secrecy of the plaintext over an untrusted network, but we also need to prove the integrity of the data, that the ciphertext has not been modified. To do that, we need to either create a message authentication code or a signed hash of the data. But here we will just compute a simple hash to show message integrity. We will start with the ciphertext data and add some kind of feedback algorithm that takes the present input on top and XORs it with the previous input at the left and runs it through some function that makes it very hard to go backward. Here is the function we will use. For any input on the left of the table, we will get the output on the right of the table. Recall, this is just a make-believe example. Real hashes would not use a table like this, but the value of using this table is that we implement a completely non-linear function, and that is something real hashes do want. So let's see how each block of ciphertext input creates a new output from the XOR of the previous output and how the hash function is applied to that output. We start with the first block, 6, which is the first value into our XOR logic. Normally, the hash function would have a previous value or an initialization vector, but we will assume it is 0. Therefore, 6 XOR 0 is 6, our first computed value. Throwing 6 into our function, we get 7 out of this round of the hash function and put it into our table. The next block is 3. So we will put that in our table and into the hash. It will be XORed with the previous result, 7, producing 4, which will be put into our table and into the hash function lookup table. The result of that is 3, which just jumped into our table. The next input is 5, which is XORed with 3 to get 6. We look up 6 in the hash table and get 7, which we put in our table. And the final round works the same way. Finally, we get our last hash value, 5. This is the hash of the entire string of numbers. Note that the string can be of any length and we will still end up with just a single number. Of course, a real hash would end up with a very large number, as we've seen before. As noted earlier, we would either have created a message authentication code instead of our plain hash, or we would sign the hash. That is, we would encrypt the hash using a private asymmetric key. However, for now, we will just send the hash across the network as is. At this point, the right-hand side will take the ciphertext and compute the hash in the same way we just saw, and the final output is compared to the value provided. If they are equal, we know that the data has not been altered in transit. There you have it, a gut level of understanding of symmetric key encryption with message integrity. Are you having fun with crypto?